We'll start talking about artificial neural networks, or ANN. That's a very, very important concept, and this is kind of the starting point of deep learning, and we will discuss about it in this lecture. So what is artificial neural network? They basically simulate the behavior of biological neurons. Okay, how the biological neurons work, that is something we need to see. See, this is a set of neurons. Okay, this is just a very brief schematic to give you the idea. So this is a neuron 1, it's a biological neuron. This is the cell, and these are the dendrites, and this is the axon, and this is a neuron 1, this is a neuron 2, and this is a neuron 3. What happens? The axons of a cell is actually touches the dendrons of the next cell. Okay, so of the neuron, and similarly, the axons of this cell touches the dendrons of the next neuron. So the dendrons, or these things, they actually are the input channels, or they accept or receive the signals from the previous cell or other nearby cells, and then the output passes to the axon, and through this they go to the dendrons of the next cell, and in that way the biological signals passes through the nervous system. So like these are the inputs and these are the outputs. Exactly that, if we model it in an abstract way, these are like the inputs which are coming to it, and these are the outputs which are going out of it. Okay, so now you see, when we see something in the world, we have this neurons fired in our nervous system, and it helps us to determine that what is something. So like if we see a dog, we can recognize it as a dog. We can see a cat, we can recognize it as a cat. Like let's say we see some numbers. Let's say these are all different ways of writing 3. Okay, 3 is a number, and although they are written in a different way, if we see that our the corresponding cells in our nervous system, they fire and then tell us, oh, these are just 3s. They match with that. Although they look different, we can easily recognize them as 3. Our nervous system is so strong. So that's why we get some inputs, we get to see them, and then fire it in the neuron system. It can recognize and then gives the output. Sometimes this can connect to the next layer of neuron and next layer of neuron in that way to make more complicated or complex decision. This is a very basic one neuron model. So we again draw this one neuron model in a more formal way, where we show that this in the left side there are multiple inputs, x1, x2 until xn, and they are kind of taking inputs and coming to that neuron which is in the middle, and the neuron is these connections are in the biological system called synapses. So these are basically the synapses for the network model, and they have different weights, W1, W2, W3 until Wn. So what are the weights? The weights basically signify the importance of a particular input, okay? Importance of a particular input for making decision. And then they are all, the fractional values. And now when the neuron gets these inputs, they make a combination of them, a linear combination. You see, sum of, Wi, Xi, that means weight times the input. Okay, so this makes a linear combination. Also, there is a bias. You see, this equation is very similar to what happens in the linear regression. Okay, so we determine the weights and the inputs and then add a bias to it. We call this whole function as a z, and then we use another function which is called the activation function to convert this particular input to map to a certain output. Okay, the outputs of a neural network can be some numerical value, kind of regression, some numerical value, continuous variable. Also, it can be binary classification like yes, no. It can be a multiple classification, like let's say a system which can handwriting recognition system which can determine 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So 10 different types. So there can be multi-class classification, binary classification, continuous variable identification. Anything is possible. Okay. So this model is called a single layer feed forward neural network model, or a perceptron. Single layer feed forward neural network model was proposed by Frank Rosenblatt in around 1950-60 that time, and then it was not that popular that time, but over the years people have found out its better usage, and they found out that single layer feed forward neural network may not be good enough, so they introduce multiple layers in between the input and the output. So this is such a neural network where this is the input layer in the left and the right one is the output layer. So the right one will have how many neurons will depend on, basically what you want to do. Like if you want to have three classification, and then there will be three neurons in there. And if you have 10 output classes, so you might have 10 different neurons in there. And all these intermediate layers between the input and the output layer are called hidden layers. Okay, they have equal number of neurons in them, mostly equal number of neurons, and each neuron will be connected to the each neuron of the next layer. Okay, like here the first one is connected to all the 5 here, second one is also connected to all the 5 in that way. I have just shown one, but each neuron will be connected to the each neuron of the next layer, and basically also of the previous layer, and that makes this a complete network. So this networks can become very, very complicated, and depending on how deep you go, it will determine the the depth of the neural network, and it's also called deep learning models. Okay, so now you see there is one important thing, the activation function, which I said this is the activation function, which takes the linear combination of the weight and the inputs as well as the bias, and then tries to convert them or map them in a non-linear function. Okay, why linear functions are not good enough? Because linear functions, it's not possible to combine them and model them as a complicated output function. Why? Because the FZ helps introduce non-linearity in ANN. So this is to comply with the universal approximation theorem, which is a very well-known proposition in neural network. Is a universal approximation theorem which says neural networks can approximate any function. Okay, any function. That means that whatever be the output function with respect to the input data stream, it can model it so nicely that the prediction will be very accurate. So it's called universal approximation theorem. Linear activation function has two major problems. Okay, so it is not possible to use backpropagation, as the derivative of the function is a constant and has no relation to the input x. We'll talk more about it when we talk about the backpropagation, but we know that the derivative of a function, which is a linear function, is a constant, and that's a problem. Now all layers of the neural network, all layers of the neural network will collapse into one if a linear activation function is used. So that means even the last layer is nothing but a linear combination of the previous layers. If everything is linear, the output is also linear. There is no way to have a higher dimensional or a more complicated function, which is kind of violating the universal approximation theorem. Okay, so no matter the number of layers in the neural network, the last layer will still be a linear function of the first layer if it's a that's a linear combination. So essentially a linear activation function turns the neural network into just one layer. How many layers you include here to make more complicated decisions, it will still behave like a single layer if it's just a linear combination of all the layers. So what we try to use a non-linear activation function. Okay, so that's the idea of the this activation function, which helps to introduce non-linearity in ANN to comply with the universal approximation theorem. So the non-linear activation function allows backpropagation because now the derivative of the function would be related to the input. Okay, and it's possible to go back and understand which weight, so you can come back. That's a back propagation. We'll talk about this more, and you can come back and adjust the weights and check which one has more importance, and then make a better decision as a result. So you can it's possible to go back and understand which weights in the input neurons can be can provide a better prediction. So nonlinear activation functions also allow the stacking of multiple layers of neurons, as the output would now be a nonlinear combination. So this output will be a nonlinear combination of this, and similarly. So it's a multiple nonlinear combinations can be stacked up. Okay, would be now a nonlinear combination of input passed through multiple layers. So any output can be represented as a functional computation in a neural network. So this will be multiple non-linear outputs combined together to make a final decision, make a more complicated final classification. So many different activation functions are possible. Okay, so like sigmoid function, we talked a lot about sigmoid function earlier when we talked about the logistic regression, and there are similar other functions like CANH, which is also a sigmoid style function. ReLU is there, leaky ReLU is there, softmax is there. So we'll probably talk a little more about them later, but for the time being they are all nonlinear functions. So for the activation function, what we do first step is just creating a linear combination of the weights and the inputs along with the bias. So y equal to mx plus b, the standard linear equation, and then which is nothing but combination of all the weights and inputs and the bias. And then at the step 2, what we do, we apply this there here. I have just shown the sigmoid function. We apply the the sigmoid function or any other nonlinear activation function to calculate what will be the probabilistic outcome, and based on that, whichever be the higher probability, we will decide that that is the main determining class for a particular given input.